Good afternoon, everyone. I hope all of you had a nice lunch, but not heavy lunch. Post-lunch sessions are always difficult to keep up with. Throughout this week, I'm sure many of you have attended so many different sessions related to SQL Server, related to performance tuning, virtualization, column store indexes, high availability, a lot of new stuff and cool stuff that is coming up, is already there in 2012. And it was really nice now, I think, to have something like indexes to go back to these original heroes and culprits of SQL Server that actually boost up the raw performance of SQL Server. And that's why this session and this title, Back to Indexes, the original culprit. So welcome all of you to my session on indexes. There is one reason why I am here, and what am I going to really talk about today is, back in India, we work with pretty large SQL Server customers. And every time I go into a performance tuning engagement with a customer, most of the times I see that indexes happen to be the bottleneck of performance. And the reason why indexes happen to be the bottleneck is not because those databases have indexes. The reason is they do not have the right indexes. That's the problem. And what I've done is packaged those learnings and those scenarios in simple, easy-to-understand demonstrations, which I'm going to show you today. One of the reasons that I've seen why DBAs, those performance problems are because DBAs do not have a good understanding of indexes, how they work, or they do not have a good understanding of the dynamics of SQL Server and how it stores data, but most importantly, the internals of Optimizer. Optimizer, being one of the most complex pieces of code in SQL Server, is sometimes not really well understood or is misunderstood as to how does an optimizer really choose a particular index. And this is what I'm really going to demystify today. So here I am. My name is Amit Bansal, and I will be your host for the next 75 minutes. I currently work as the Chief Technology Officer of eDominer Systems and Peopleware India. I'm also the president and founder of SQLServerGeeks.com. And I'm also an MVP of SQL Server, and if you want to know more about me, you can visit amitbansal.net. Apart from the work that I do, consulting training on SQL Server, I just love this product, and I have been working with this product since version 6.5 in various capacities. So what really are our takeaways? So today when you walk out of this room, really what I would expect all of you to have answers to these questions. You would know how the optimizer decides to choose a particular index, optimizer's choice of using a physical join operator. Which physical join operator should the optimizer use? And I'm sure some of you might be wondering, where does physical join operator come here? Yes, it is indeed important, and I'll tell you how is it related with indexes. Database tuning advisor. We'll talk something about database tuning advisor, but I don't want to disclose that right now, so let's be on hold for some time. And last but not the least, getting rid of redundant indexes. These are going to be your takeaways. And I have a special request, a special ask to all of you. If you think that we meet these takeaways, and we're going to talk in depth about some of them, then please go and submit feedback. That is very, very important for all of us. This is the last day of TechEd, and I know it has been tiring. You might have walked up and down this big building n number of times. I don't know how many miles you might have walked by now. But yes, if we meet the takeaways, it will help us improve, and it will help us deliver better to you. So please do that. That's my ask of you. Take a deep breath and have a look at this. This depicts endurance. This depicts tolerance, cooperation, and most importantly, this depicts resource utilization. This is what really represents how the data is stored with organizations today, and I always use this as a metaphor to explain indexes. Now, jumping onto this truck is like inserting data or updating data, right? Moving out of this truck is like extracting or selecting data. And most importantly is if I tell you to find where my bag is on this truck. And when I say my bag, one of my speaker colleagues down at the SQL Server booth told me, Amit, is this how you travel to the airport? And then I asked, are you asking me travel to the airport in India or in US? And he said, of course, India. And I said, no, this is how I travel. I traveled in transit, just to save both the sides. Okay. So this is really the metaphor, and that was just to depict what really indexes can cause, the kind of performance problems that indexes can cause. So I have broken down this session. This is going to be a demo-heavy session, and I have broken them down into a couple of categories. So we will right away start with an indexing scenario, followed by talking a bit about the optimizer and when it chooses a particular physical join operator. We move to the next indexing scenario, and we consider good designs versus better designs. And we'll talk in depth about the optimizer's choice of indexes, followed by a third indexing scenario. And all these three indexing scenarios that I'm going to talk about in demo today are interrelated. So they're not isolated, they're interrelated. Last but not the least, we'll see how to get rid of redundant indexes, and we'll do a cleanup act. So let's begin straight away with the first demo. And as I said, I have packaged everything into simple, easy to understand demonstrations. We are using AdventureWorks database. In AdventureWorks database, there is a table person.contact. Let's look at this table. This database is freely available on codeplex.com for you to download and practice all my demo scripts. The reason why I'm showing you this table is we are going to focus on 3 columns here: contact ID, first name, and email promotion. There are a couple of other columns out there, but we will not use them in our demos. The first thing that I want to do is make a copy of this table as contact2. This is a heap. I make another copy of this table as contact3. I create a clustered index on contact2. My clustering key column is contact ID. And I create another clustered index on contact3, clustering key as contact ID. Now what I have is 2 tables, contact2 and contact3, and these are, let me use an informal term called clustered tables, right? Tables with clustered index. I have a requirement to design an index to satisfy this query. Now, I've really made this query as simple as possible. This query is just joining 2 tables, and the joining key is first name. And as you know, we do not have any index on first name right now. When I run this particular query, and I get the output, and I have not put any filter, let me include the actual execution, that I have done that. And if you observe, we have a clustered index scan for both the tables that gets joined here using the hash match operator, right? Now, hash match physical join operator does the heavy lifting. As you know, there are 3 physical join operators: the nested loop join, the merge join, and hash match. And I'm going to dive a bit deep into these physical join operators in some time. Now, all is good till this point of time, when optimizer by default chooses hash match. It doesn't go for nested loop, it doesn't go for merge join. The reason being, both the inputs are pretty reasonable in size. The optimizer or SQL Server implements a hashing technique where it builds the hash tables in memory, right? And there are 2 phases when it comes to hash match: the build phase, where it builds the build table, and the probe phase. The only problem with hash match at times is, you will see hash match as physical join operators in many data warehousing queries, is if you are short, if your box is short on memory, the tables that are created in memory may be spilled down to work tables in TempDB. Now, considering that this was a query that was running out of a departmental report or something, and one of the business owners said that they want to order the data, right? And you put the order by clause here, right? When you put the order by clause, let's see what the optimizer does. Any guesses? Do you think it will still take hash match? Any guesses? So if you look, what the optimizer has done this time is it chooses merge join, not the hash match. Now, there is a reason why optimizer is a cost-based optimizer. The other alternate of this could be that the optimizer puts up a sort operator here, right? So after the join is done, it does the sort and sends the results back to the client. It doesn't do that. It instead sorts the inputs, right? And then uses the merge join operator to join the data and send the results back to the client. Now, notice the reason why it is now it implements a sort operator and then changes the join operator to merge is because merge join has two prerequisites. Prerequisite number one, the inputs have to be sorted. So it does that by implementing the sort operator. And prerequisite number two, you need to have an equality operator in your query. So we have an equality operator on the join keys. Now, what I want to do is implement an index which can improve the performance of this query. Now, this is really trivial if you look into the example. And to just really quickly show you, this is the original query that I have pulled out these examples from. And as I said, I'm implementing a simplified version to explain these concepts. So back to the example, before I create the right indexes for this query, what I want to do is record update performance. Now, this is very critical. Many times when we go to these performance tuning engagements and when customers complain about performance, the first thing that I ask is, where is your baseline? Have you recorded performance metrics before? Many of the customers would not have performance metrics. If they have, they would be skewed, or they would be really obsolete. And I always tell my customers, it's so difficult to troubleshoot troubleshoot SQL Server or any performance problem if there are no baselines or if there are no metrics. So what I'm going to do is, before I implement an index or I implement a series of indexes, I first want to record some performance metrics. What I want to do is basically, now these are two statements, dbcc drop clean buffers and free proc cache. If you're tired of your job, you can run these statements in your production environment. So what I'm going to do is run these statements. Just to be fair, I want to run these statements, clear up the memory, and fire an update statement. What this statement is going to do is simply update all the records and set the first name to Amit. I'm going to record the time before I start the update, and I want to record the time after I start the update. And I will take down some numbers. So when I run this, it takes about 141 milliseconds. What I'm going to do is, I'll record this here, and we will have this query window open throughout our session. 141 milliseconds is our performance. This is our performance when we do not have any non-clustered index, right? We only have table with the clustered index. Let's go back. Now, the right index for this one will be, if I create a non-clustered index on first name, both on contact 2 as well as contact 3. When I do this, what will happen is, because there will be a non-clustered index, the data, this first thing, this will be a covering index, because that's the only column I want out of my query, and it is going to sort the index, the data in the index with first name. Let's go and create these two indexes on contact 2 and contact 3 respectively. When I do this, and if I run this statement back up again, okay, so I will have to quickly drop the objects and create them again because I updated the tables. So let me do that very quickly. Make a copy, create both the clustered indexes, and create the non-clustered indexes. And if I run this query, now what I would expect is, in the execution plan, I will get rid of the sort operator, right? Because, and if you observe now, I'm doing, the optimizer does an index scan, but this time it scans the non-clustered indexes that we have created. What is the performance improvement that we have got? So let's quickly run these two things as a batch. And in the second one, I am forcing a hint so that optimizer uses clustered index scan. So in the first case, because we have a non-clustered index, we will not have the sort operator. In the second case, we will have the sort operator. And your performance difference here will be, did you see that? Did you see that 100 versus 71? Can you have something like this in SQL Server? No, this is simply a refresh problem. See, it is fixed now. 29 versus 71, just a refresh problem. So there's no bug. Don't go and file a bug now. Or else if I would have shown something like this to someone, say go to connect.microsoft.com and that's the place. So this is the performance improvement, 29% versus 71%. Now this example is a pretty simple example that I showed you, and I'm going to follow up with this on this example with a more complicated one in the next demo. Back to the concepts. What you have really seen is, I talked about, now this is really what I wanted to focus on, is how is the physical join operator related to indexes, right? Because you have the right indexes, SQL Server utilizes that indexes, and it helps in improving the performance using the merge join operator. Just to compare all the three join operators, the nested loop, the merge, and hash, nested loop's cost is really input A multiplied by input B. It compares every record from input A with every record from input B, and there are no prerequisites. And most of the times you will see nested loop join in OLTP environments. Coming to the last one, hash join, there's only one prerequisite, that you should have an equality operator. The inputs need not be sorted, and you saw an example of that. As I said, hash join does the heavy lifting, and it is pretty common in data warehousing environments. And what we did was merge join, which is good for medium to large inputs, but these guidelines like medium to large are very difficult to quantify, and it works in different environments differently. There are two prerequisites. It requires the equality operator, and the inputs need to be sorted. One thing about the cost of merge join operator, the cost of merge join operator simply in terms of units is the sum of input A added with the sum of input 2. So the sum of both the inputs is the cost, really, because both the inputs are sorted. So every record from input A need not be compared with every record from input B, because if a particular record does not match higher up the ladder, there are no chances that it will match lower up the order. And that's why merge join is really good. But this being said, I'm not trying to pass on a message that merge join is better than nested loop and hash join. That's one of the biggest myths and misunderstandings that sometimes DBAs and developers have. And I always get this question, which join operator is good? Well, the answer is it depends. It depends on an environment. There is no physical join operator is good or bad, period. So what we have covered is first two aspects. We have looked into a simple indexing scenario, and we have looked into the join operators. Now I will move into the next indexing scenario, scenario number 2. And this is where I want your inputs now. We had two tables, right? Contact 2 and contact 3. Now for the moment, forget contact 3. Rest of the focus would be only on contact 2 for the rest of the session. This particular query, have a proper look at this query. I want to design an indexing strategy that will satisfy this query. Couple of things I would request you to observe here. First thing is the different operators that I'm using. So I have 3 filters on first name, email promotion, contact ID. I use the operators like, equal to, less than. Option max.1 is just simply to make sure that I'm only using a single processor for execution. And I want contact ID, first name, and email promotion out of this query, which means one thing is for sure that we would land up creating a covering index. Couple of other things, selectivity. If I only run this query with first name as a filter, only on this particular predicate, 872 records are going to be returned out of approximately 19,000 records, which will give me 4.3% of selectivity. If I only run this query with email promotion equals to 1, it gives me approximately 25% of the data. And if I run this query only with contact ID less than 10,000, as you know there are approximately 19,000 records, it gives me 50% of the records that are being returned, right? Just to show that quickly to you, here is what I meant. First like L on first name, 872 records, which is really 4% of selectivity. Email promotion equals to 1, which will give you 5,000, which is 25% of selectivity, and the last one, contact ID, which will give you about 50% of selectivity. This being said, I have two options for you, option 1 and option 2. And I'm going to ask you which option do you choose. In option 1, the only difference between option 1 and option 2 is the order of columns. In option 1, which is contact composite 5, first name is the leading column of the index, right? Keep the selectivity and the operators in mind. And in the second option, contact composite 5, email promotion is the leading column of the index. I don't want answers from you, but I'm sure I want all of you to choose one of these two options. Okay? I will come back to you in a while. As a DBA, and it's a recommendation from Microsoft, the quickest and the best thing you can do is submit this query to Database Tuning Advisor and look at the recommendations, right? Let's do that. So I will kickstart SQL Server 2008 R2 and performance tools, Database Tuning Advisor, connect. My query DTA. I have put this query in this file dta.sql, tune adventure works. This is the database I took, and I'll start the analysis. Database Tuning Advisor is a good place to begin with, but you may follow the recommendations, you may not follow, depends on what recommendations you get from DTA. Sometimes it gives good recommendations, sometimes it gives recommendations that will really irritate and frustrate you. So here is the recommendation. It tells you to create a statistics. I'm going to ignore this for the moment because statistics is not my focus right now. I only want to focus on indexes. When I create indexes, the necessary statistics for those indexes will automatically be created. The second recommendation that comes from Database Tuning Advisor is to create the non-clustered index, right? And this non-clustered index, the recommendation is that first name should be the leading column, followed by contact ID and email promotion. Now, contact ID in this case is not important because contact ID is our clustering key, and any clustering key will automatically be included in every non-clustered index. So really it boils down to first name and email promotion. First name and email promotion. Going back to the options that I had presented you, first name and email promotion is contact composite 4. Now, some show of hands. How many of you selected contact composite 4? How many of you? 50% of you? Okay. And how many of you selected contact composite 5? Okay. About 20%. That means rest of you did not select anything? Okay. Okay. So if you still have to make a choice, make a choice. Now, what I am going to do is open up all the indexing options for this query. And this is going to be really interesting. So I had all these indexing options. Okay. Welcome to index tuning. Okay, so, but we are only going to focus on the last two, which is our option 1 and 2. Basically, the numbers here are 12 and 13, but that's fine. Contact composite 4 and composite 5. Let's go and create both the indexes, and let's see which index does the optimizer choose. I execute them, back to my query. So I can close this and query to be indexed is this one. Okay. So this was the query. Now when I run this, include the actual execution plan and execute this query and look at the performance. So the optimizer chooses contact composite 5. It does not choose contact composite 4. Now, those of you who thought contact composite 4 was the right index for this query, you're not wrong. You're absolutely right. That was a good design, but having email promotion as the leading column of the index in contact composite 5 is a better design, right? And this is what I really want to show you in my next demo on good design versus better design. So let us first see what is the performance difference between contact composite 5 and 4. So out of these two popular choices, I put an index hint here, contact composite 4, and I run both of them together. And when I look at the execution plan, you will see 62% versus 38%. That is the performance difference. And really the crux of my demo here is to make you understand why is optimizer choosing contact composite 5 versus composite 4. So let us look into the execution plans and the, just a minute, let me pull out. Oops, sorry, I I messed up these. Yeah. If I look into the execution plan of both these indexes, and I hover my cursor over the tooltip, and because I can't do both of them together, I've put them onto the PowerPoint slide. But observe what really happens in Contact Composite 5. If you observe, there is a seek predicate here. It prefix email promotion, right? So what is Optimizer doing? It is actually seeking on email promotion, right, which is the leading column of Composite 5. And it further seeks on first name. So if you can see, first name, scalar, operator, and less than m, because our first name was like L%. The rest of the stuff, which is contact ID, goes as a residual predicate. So here, really the rule here is, if you have an equality operator in a multi-column index, if you have an equality operator on the first column of the index, it can also seek on the second column of the index. This is what really happens with Contact Composite 5. With Contact Composite 4, however, if you observe, there is no prefix. So there is the only seek that really happens here is with, and which is actually kind of a range scan, is with first name, and starts at operator, if you see, starts with the letter L and ends before M. And the other columns, which is email promotion and contact ID, goes as part of the residual predicate. So you can see email promotion here, and you can see contact ID, which means in Contact Composite 4, the optimizer is only able to seek on first name. It is not able to seek on the other columns that are there as part of the index. Really, how this works is a bit about the statistics here. Now, going back to Composite 4, which was one of your choices, is most selective column should be the first column. That's the typical guideline that really comes across, right? And I think, was that the reason many of you went with Composite 4? Yeah? Most selective column. Now, as I said, that's not a wrong guideline. That is absolutely correct. The only problem is sometimes that guideline is not explained properly, or other caveats are not included as part of that. So if that was really true, and does it mean that if you add primary key as a leading column of all your non-clustered indexes, you will have tremendous performance improvement? Obviously not. You will in fact have degraded performance when you do that. So what really happens behind the scenes, and now let me talk about statistics and all the permutations and combinations that the optimizer actually evaluates. So SQL maintains a histogram only for the first column in the index. That's point number one. So let's go back and look into the histogram. So if I look into the histogram of Composite 5, you will see range. So there are only three values, 0, 1, and 2 for email promotion, which makes a density of 0.3. Now, SQL Server, the optimizer, only has a histogram for the first column of the index, but it has density factors for all the columns that are part of the non-clustered index using a left-based subset mechanism. Density really here is how many distinct values are there in a particular column. And the density factor is really calculated by 1 divided by the number of distinct values. So if I have 3 distinct values in email promotion, I get a value of 0.33. So which means that if you only have histogram for first column, and if that column is not selective enough, chances are that optimizer will not use it. So optimizer only knows the distribution of values only for that first column. But if you have equality operators on the first column, second column, and all the leading columns of the index, chances are, on an average, the optimizer would know the number of records that are going to be returned by the query. Which means, and let me just prove that in a moment, which means if I go back and change the, instead of like operator, if I put equality operator here, and if I put equality operator here, and email promotion has equality anyways, and I compare the performance of both of them, I will see an execution plan with performance as 50-50. Are you getting the message here? So really the crux here is, if we go into the rules of optimizer's choice of indexes, this is really how it works. So if the optimizer on a single column index, optimizer can seek on first name, email promotion, and contact ID in all these three examples, whether you're using the like operator, you're using the equal to operator, or the non-equality operator. Look at the last three examples where the optimizer will not be able to seek on a particular index if you have %L as part of your like operator, using functions like ABS, which really does not make the index arguable, so it won't use that. And if you have a computation even before the seek could peep in, which is contact plus less than 10,000. Which means if I, just to show you, if I tweak this query a bit here, and instead of, and suppose if I put ABS on email promotion, and this particular query was using contact composite 5, and when I run this, if you observe, this is now not seeking on 5, it is seeking on 4. The reason being email promotion is the first column of contact composite 5, and I have I'm computing the absolute value using the ABS function, which means the optimizer cannot seek on it. Understanding the single column index and how it works, the choice and the preference of optimizer is pretty straightforward, but sometimes the intricacies really lies with the multi-column index, and I want to spend some time with this. So look at the first point. The index can be used to seek on the second column if there is an equality predicate on the first column. And this is what is really happening in our scenario. In our scenario, if you look at the first example, which I say is true, first name is equal to L and email promotion is equal to 1. Then if I am actually writing a query like this, then my index is what we call as fully seekable. So it is able to seek on email promotion as well as on first name as well as on email promotion. Partially true if first name is like L% and email promotion is equal to 1. And of course, you cannot seek on this particular index, the last one where first name is like L. So if you can't seek on the first column, you definitely cannot seek on all the other leading columns. Just to digress a little more into the partially true, that is the second one, first name like. So there is no equality operator on this first column, and that is the reason why you're not able to seek on email promotion. Now these are some of the common scenarios that I have seen with customers, and obviously in many cases it has been multi-column scenarios that I talked about, not much on single column scenarios that I wanted to talk about. Coming back to the selectivity and the statistics, so histogram is one aspect, the density is the other aspect, and statistics are really critical for the optimizer to estimate the cardinality of the number of records that are going to be returned by the optimizer, and then they play a very important role. So how I've really tweaked the guideline, the last point on common guideline, it should be like most selected columns should be the first column when all other column predicates use the equality operator, which was not the case, which was not our case in this particular example. So in this particular example, we had first name in contact composite 4, you have first name as the leading column, but it is not using the equality operator. And that is why the optimizer goes and chooses email promotion. So let me just correct this back again, email promotion as contact composite 5. So with this, on the optimizer choice, single column and multi-column index. And really, when we are talking about the equality operator here, how would be the scenario when it is non-equality operator? Well, non-equality operator is going to be trivial. The reason being is as simple. If the optimizer cannot seek on a column which has the non-equality operator, then if the first column itself has a non-equality operator, then all other leading columns cannot participate in the seek predicate. So, and they all become the residual predicate. So non-equality operator here really is trivial. The crux really is that in a multi-column index, please pay attention not only to the selectivity, but the like operator, but the operators, both equality as well as non-equality operators that you have in the other columns that make up the entire index. That is one of the important lessons that I wanted to send across using this particular demonstration, which is scenario 2. So just a quick summary on contact composite 4 and 5, and it helps to put them side by side, and you can clearly observe the seek predicate in, seek predicate on composite 5, and you can see there is a prefix happening on email promotion, followed by on the first name. Residual predicate goes as contact ID. In case of composite 4, you're only doing a seek and a range scan using the start and the end that you can observe on first name, and you have the residual predicates of email promotion and contact ID here, right? That's the crux of multi-column index and the optimizer's choice of which index it should go with. What happens to the DTA? So database tuning advisor. Now, the message that I'm sending across is not that DTA is not good or you should not use it. Database tuning advisor is a fantastic place to begin with. All I want to recommend and tell all of you is do not follow the recommendations of DTA blindly. It's a good starting point to get the basic set of recommendations, and then you can build on top of it. That's the real idea of having DTA as a place. It's not the final decision maker. UDBs are the final decision maker. It's just a helping tool to you. And really in one of my earlier conferences, one of the audience members asked that, then why is DTA not giving the right recommendation? That's the question. DTA is actually built on a Microsoft research paper that was published years back, and how it works really is it definitely uses the statistics that are there. It does sampling of the data that's there in the table, and it creates a lot of hypothetical tables and indexes in background to give you that recommendation. So really, it's a good starting point to begin with, and then you have to build on top of it. So with indexing scenario 1 and scenario 2, where our tables are, contact 2 and contact 3 right now is, we have 3 non-clustered indexes, the one that we created for indexing scenario 1, and we have 2 non-clustered indexes, one on composite 4 and the other one is composite 5. And now, because we know that composite 5 is the one that we should have, we should actually go and drop composite 4. So what I'm going to do is, from index options, I will go and drop composite 4. Oops, drop composite 4 is this one, okay? Demo heavy session, back to indexing scenario 3. And in this indexing scenario 3, what if we tweak the original requirement? So originally we had a like operator here and we had an equality operator here, right? I just tweaked it a bit, and I have put first name as an equality operator equals to L, and I've put email promotion as less than 1. Now, going by all the learnings that we had in the last few minutes, this means if I run this particular, now I have the first index and I have composite 5. We have dropped composite 4. Let us run this and see what the output is. And if you look into the execution plan, I'm not getting anything in a moment, I will tell you. If you look into this, it actually is not using composite 5. It is actually using the index that we created right in the first demo. So what it does is, it basically seeks on first name equals to L, and then because we want email promotion and contact ID, it does a bookmark lookup. So sorry, I did not zoom. So it seeks on first name index that we created in the first demo, and then it does a bookmark lookup to get you the data out, right? But will this be the case always? If you look at the result sets right now, you have no record being returned. And what is our data like? Let me select star from person dot contact to is, okay. So will this always be the case? Because selectivity is the key here. how I have tweaked this requirement, the same query, but this time I've changed the predicate values. I've put first name as Lucas, and I've put email promotion as less than 3. So if you compare these two queries, and I get rid of contact ID, and if I run this particular query, this time it falls back on composite 5. Because really the selectivity is key here. The reason being, in the first case, the query was highly selective, which was, it was really returning no or very low number of records. So bookmark lookup was more efficient. But in the second case, because it's returning approximately like 9,300 records, bookmark lookups, having 93 bookmark lookups is expensive. Again, it's optimizer, it's cost-based optimization, and it considers this execution plan to be more cost-effective than the other one. So what it does an index scan of composite 5. Right? Now, given this scenario, and really this is the most trickiest part that we see with customers when you have this variety of queries that are coming in, and that gives you variety of results, sometimes highly selective, sometimes very low selective. In order to now, suppose, let's assume a hypothetical scenario that the way these incoming queries from client applications and from reports are kind of equally distributed. What I would do in such a case is go back and create composite 4. When I go and create composite 4, because in composite 4, first name is actually the leading column. And going back to the query, because I have an equality operator both on first name in both of these queries, chances are that composite 4 will get picked up. So when I run this query, where the result set is highly selective, it uses composite 4. And when I run this query where the result sets are again not very highly selective, that is, it returns more number of records, we still get optimizer picking up composite 4. Now here is the summary. If you sum up all of this, scenario 1, we had a very simple query and we created a covering non-clustered index. We moved on to scenario 2 and we had two choices, composite 4 and composite 5. We decided to stick with composite 5 because it was a multi-column non-covering index, and email promotion was the leading column of the index where we were using the equality operator. The other columns were non-equality, so SQL Server decides to use that. We stuck with composite 5. We have another departmental query or a business requirement coming in which actually gets really satisfied with composite 4. Now we have 3 non-clustered indexes here, 3 non-clustered indexes, and see how they become the culprits of performance. So what I'm going to do now is, having 3 non-clustered indexes here, I'll go back to my update, okay, and use AdventureWorks. And to be fair again, because all the pages, data pages are in memory right now, we drop them and clean the cache and run this query, update query again. And look at the number, 1472, which is still better than 1705 when I recorded it last, 1472 milliseconds. Look at the update performance, and update performance, as all of you know, is so critical when it comes to OLTP environment, right? Here is the place where you need to strike a right balance. As you keep on going, creating more and more non-clustered indexes, your update performance is definitely going to go down. And absolutely, as a DBA, more overheads really get added because you have to maintain them, rebuild them, defrag them, so on and so forth. But here is the real performance bottleneck now. 3 non-clustered indexes, and I understand the DBA's pain because I have been in your shoes for quite some time. It's really a very taxing thing to tune indexes because this is not a one-time job, it's an iterative approach. You need to keep monitoring, you need to keep looking into where are those duplicate indexes, where are those redundant indexes, and how can you get rid of them to really strike a right balance between your select and your update. So what you have done here is really created 3 non-clustered indexes to give 100% best performance to all these 3 queries, but your update performance has drastically gone down. Okay? It has drastically gone down. So what we need to do now is, too many non-clustered indexes is what we have. Okay, so yeah, those are the sources where I get all these pictures from. Too many non-clustered indexes is what we have, and we need to strike a right balance between select and update. And the idea here is to get rid of redundant indexes. And this is where the typical challenge is, because SQL Server does not have an automatic way of identifying duplicate or redundant indexes or DMV as such. This is pretty much a manual thing that you need to do, which is constant monitoring of your incoming workload, constant monitoring of the utilization of your indexes. And there are some DMVs, missing indexes, DMVs that can help you, DMV usage stats that can help you to identify if an index is being used or when was it last used, so on and so forth. So I'm not really, I can't really go into the constant monitoring and performance monitoring aspect of it, but yes, that's what you need to do. So given these scenarios now, the 3 indexes that you have, let's sum all of this up and get rid of some redundant indexes. And this is where really the culprit aspect of indexes come into play. How many of you were wondering that why am I calling indexes the culprits? Because indexes are supposed to improve performance, right? That is because I can't and I don't want to call DBAs the culprits. It's because then some of you might get angry and give me bad scores. So yeah, really, on a more serious note, what really I have done is, gather all these. Most of my customers have, they're big customers, big SQL Server deployments, big data, big queries, big execution plan. And I always like it how you can explain complicated problems, big problems in a most simple, easy to understand manner. And that's why AdventureWorks was the best database I can actually use to replicate those real life problems into these simple, easy to understand concepts. So back to this last aspect, I want to get rid of some of these non-clustered indexes so that my update performance is good. And really how this is I would evaluate. And I'll tell you, there is no really good any guideline or thumb rule as to how should you approach removing redundant indexes. But I can just talk about a few things. First is, who are you running this workload for? Who is that person? Is he an important person in your organization, right? Political. So answer that question politically. So if it's your CEO, vice president, so on and so forth, then have all the right indexes in place so that the reports just run in a flash of a second. But then keeping that aside and coming to more technical aspect is, you have to look at the frequency of these queries that are running in. So if I have these 3 different workloads, what is the frequency of these workloads, right? Certainly, you want to have the right indexes in place for workloads that are more frequent than the others. Point number 1. Point number 2, you need to observe and monitor the selectivity of these workloads. Because as I showed you in the previous demo, how based on the selectivity of data, the optimizer chooses different index. So you need to keep a track on that. And third is the toughest aspect is really the manual monitoring and evaluation of the indexes that you have. And we have worked with, tabular formats and structures where we put down the index, the cost estimates, so on and so forth, trying to figure out that if a particular index really gives best performance for a particular query, which is the next alternative index that can give equal or close to that kind of performance. And this is what we are going to do in this one. So let's begin with the second one here. In the second case here, where we have first name equal to lane and email promotion less than equal to 1, we have inequality operator here. And contact composite 4 was the right index for this one. Correct? Now, if you observed, this was really, if suppose contact composite 4 was not there, we created it later, right? If contact composite 4 was not there, this query was falling back on this one. Make sense? Let me number them, if my mouse works pretty good. 2, 1, 2, and 3. Okay? So this particular query was falling back on this one when we did not have composite 4. But when this only happened when the query was highly selective. But when the query was low selective, this particular query fell back on composite 5. Right? Now, and composite 4 really was the index that actually works best for this workload in both the scenarios, whether the query is highly selective or whether it is low selective. So I want to keep composite 4. I want to keep composite 4 for another reason. I'm not jumping to conclusion, but for another reason that first name is the leading column. And why I want to stick to composite 4 is because this particular workload, our first demo, was highly dependent on this index, where first name is the leading column of the index, which means if I drop this index, this particular workload can be satisfied by this index. All I wanted to do in that execution plan was to get rid of the sort operator, right? And I can get rid of the sort operator if I have an index on first name. So my third workload, so this particular workload can depend on composite 4. This one will go to composite 4, which means I can get rid of this one. Now, the real question is, what do I do with composite 5? Now, that's the choice you need to make. You want to keep composite 5, keep composite 5 if your update performance is not being complained by your users or the users of your application. Or what you can do is, if the performance difference, those numbers, are really not too high between composite 5 and composite 4, you can get rid of composite 4. Make sense? So what I am going to do is, last is on the cleanup act, and I will go back and, so here are all the indexes that we have, and I'm going to get rid of this particular index, C2 first name and composite 5. Drop both the indexes and record the update performance. To be fair again, dbcc drop clean buffers and free cache, and I fired the update query. 303 is my performance. So this is how the numbers work, and these are just basic numbers. I'm not trying to show what you should record and what you shouldn't, just for the purpose of the demo and the illustration. So when we had no non-clustered indexes, our performance was 141. We had 3 non-clustered indexes, it shot up to 1472, back to only the required index, but with a little bit of sacrifice in the select, because we dropped composite 5 also, we get 303 milliseconds. So the idea here was to show how indexes can improve performance, at the same time how they can help you in degrading performance and what you need to do to rectify them. Okay, I have some time with me, so what I'm going to do is pull up 2 more slides and talk about some I/O statistics here. In one of my in previous demonstrations, in a similar conference, one of the audience had a really interesting question, and this is going to be really interesting. What I will do is to show that to you. I will have to just drop the objects once again and make another copy, create the clustered index, go to indexes options, create both 12 and 13. Back to our second demo, when we were comparing the performance of composite 4 and composite 5, one gentleman in the audience identified about the I/O. So let me just statistics I/O. Okay. And when I run both of them, if you observe, I get 6 versus 3 logical reads. So composite 4 gives me 6 logical reads, and composite 5, which is the default for the optimizer, gives me 3 logical reads. And the question was 62% versus 38%. Is this performance difference because of the I/O? What's your take? Yes or no? Yeah? Okay. So, sorry, unfortunately, the answer is it is not because of this I/O. Now, these logical reads, 6 and 3, are execution statistics, right? After the query has executed, what have been the physical reads and logical reads. The numbers that you see on the execution plan, 62% and 38%, are estimations. They are the cost estimations. The optimizer has no knowledge of how the data is stored. So how the optimizer really works is it's highly dependent on statistics. It does the cardinality estimations to figure out the number of records that would be retrieved by a query. Then a lot of mathematics is applied to actually get these numbers that you see on the tooltip. All these numbers like 0.041 and subtree cost, so on and so forth. But it would be interesting to note one of the metrics here, which is estimated IO cost. If you look into the estimated IO cost of composite 4 index, it is 0.00460. And the estimated IO cost for composite 5 is 35242. That is 3125, which means the estimated IO cost for composite 4 is higher than composite 5. But please do not correlate both of them, right? Because 6 versus 3 is the execution stats, and these are just estimations. And when I talked about that mathematics that takes place inside the optimizer, is definitely it calculates the size of the row, the number of rows that could be there on the page, and estimates how many pages could be read, right? So it's not really directly correlated, right? But it just gives you these estimations. And why do we get 6 versus 3 number is simply because the way the data is laid out. And that's why I pulled up these slides to quickly show you. In case of composite 4, what really happens is, because first name is the first column, the leading column, followed by email promotion, this is how the data gets laid out. So I'm just taking an example of L because we used L as a value there. And it actually, because where email promotion is equal to 1, so the way the data is laid out, because the data is sorted by first name, then followed by email promotion, you have value 1 being scattered across the pages. So what the storage engine does is lands up reading all the 6 pages. But in composite 5, because email promotion is the leading column, and when email promotion is the leading column, the way the data gets laid out is it only lands up reading these 3 pages. That's why you get 6 versus 3 logical reads. And to quickly prove this point, you can always take this IO stats to quickly show you how it works. Is in composite 4, this is how the data is. First name is the first column, and if you scroll down, you have ones coming up here, and all the way down you have ones there. The data is spread across 6 pages. That's the number of pages that it has to read. And in composite 5, I am selecting email promotion and first name, only these 2 columns, order by email promotion and first name, to show you how really the data is laid down on the indexes on composite 5. Email promotion is first. So what it has to do is, because it can seek on email promotion, it skips all that, obviously, and goes all the way to the point where you have 1, and then starts scanning. And it only lands up reading data until this place, which means it is only reading 3 pages. The reason why I'm answering this question is because when you go back and look into the recording or download my scripts and play around, you might have this question. So I thought of answering this thing in advance. You can always prove this by creating these 2 tables, just to quickly show you, and I'll do that real quickly, table 1 and table 2, and I got this only the index data into table 1 representing composite 4, and composite 5 will be represented by table 2. Observe that I get email promotion and first name here, and in the previous case I get first name and email promotion, just to quickly show. And to simulate, and if you run an index stats on both the tables, you will observe that there are 5 pages for both of them, right? But we got 6 pages read because that's a non-cluster index, which means it's a B-tree structure. Right now table 1 and table 2 are heaps. So in order to really simulate composite 4 and composite 5, I will go and create 2 cluster indexes on these 2 tables, and if we pull out the data from them, including the execution plan, and sorry to scroll up and down, but where is my set statistics IO in this code? Is here. Okay, and all the way down to execute the data. This is how you would get message on both the tables, 6 versus 3. Just to prove this a little bit, you might have this question coming up on when you try to correlate the logical reads with the estimated IO cost that you saw on the tooltip. So they're not really directly correlated, and that's how the data is laid out on these non-clustered indexes. So that was when reading on the heaps, and then when I put them onto, so it reads only these 3 pages, but technically, more technically, we are also reading the root page, which I try to demonstrate with table 1 and table 2. So, call to action with this session. First thing, browse this recording once again, because I have shown like too many demos and too much of flipping from slides to slide and the screen, so you may want to watch this once again. And I'm said that you will have these this recording available to you in 24 to 48 hours. All the slide and all the scripts and demos are already uploaded on SQLServerGeeks.com. All you need to just do is go onto this website, and you will see an announcement has been posted by me, and I have posted a blog also. You can download that. That is readily available to you. Please try out these code snippets. Before you really jump to all the conclusions that I talked about, you need to first redo all that, understand it, review your indexing strategies in your environment, try to figure out the bottlenecks and any learnings that you have from this session, try and implement that knowledge in your environment. That I would recommend you to be the best way to proceed forward. And please be bold. Do not worry about trying various other permutations and combinations. It's only when you test again and again in your test environment with the absolute cost and the relative cost, when you compare multiple queries, multiple indexes, do you come out with these recommendations, and you figure out which index is going to work best for you. So the takeaways, and I hope you have good takeaways with you when you're leaving this room. That is, how does the optimizer decide which index to use, right? The equality and the non-equality predicates, optimizer's choice of physical join operator, database tuning advisor, good to use, but that's not the final decision maker. Please have your own learnings, a good way to start, but then follow your own learnings there. And yes, monitoring is the key, so please keep monitoring. Last but not the least, getting rid of redundant indexes. And that one slide where I actually showed you all the 3 queries with their indexes was the crux. That's the tough part to figure out. And that's one place where DTA has been very helpful, because it's just not about one query or one workload. You have dozens of workloads, and you have so many databases to deal with, and DTA really helps there when you are able to input that SQL file into DTA and get all the good recommendations to begin from. With this, yes, if you think I've met those takeaways and the objectives, please go and fill out the eval forms. Of course, more so if you want me to come back again and give you some more demonstrations next year. So with this, I'm ready to answer any questions you have. I would humbly request you to use the microphone. Any questions? Yes.
Can you actually detail a bit on tipping point for an index? The tipping point. I mean, you get the index used, and all of a sudden it's not used anymore by the optimizer.
Okay. One of the main, okay, so the question is the tipping point. So what I mean is, optimizer is using it and suddenly stops using it. There could be multiple reasons. Reason number 1 could be the selectivity of the query has changed, right? The query was low selective or high selective and has become otherwise now. Reason number 1. Reason number 2 could be that you now have a different, better index in place. Because for optimizer, end of the day, what it boils down to is the cost factor. The cost of using index A versus the cost of using index B. So if index B is good, it will use index B, or it will use index A. That's what my understanding is. Any more questions? Yes.
So just so that I understand, I'm coming from an SSIS background. So when I'm loading to try to figure out what indexes I should use and the pain that it's going to cause me from a loading perspective on my table, I should start off without any indexes and get a baseline first, right? And then see how long is it, what's the impact, the baseline impact on updates, inserts, everything.
Yeah.
What's the baseline impact on my most of the queries that are hitting my tables.
Right.
And then work out from there, checking out how each index adds time to my updates, but takes time away from my query selection. Is that the...
Yeah. Your understanding in the perspective of bulk load or SSIS is absolutely right.
Okay.
You can begin, you should begin with dropping all those non-clustered indexes and even the constraints for that matter, so that if you really want to boost up the performance of your workload or SSIS ETL, and then you can create those objects again. So yeah, I go with that.
Okay.
Yes. I have some of my community cards here in case you're interested, and those are my, okay, that's track resources. Okay, so last day, but then still you have some hours left over if you want to evaluate some more hands-on labs or certification area. And the resources that all of you know, Learning, Microsoft Learning, the TechNet, the MSDN, and my TechEd portal. And that's my contact. Again, I am on Twitter, _Bansal, and my email ID is ab@amitbansal.net, and the community cards are here in case you wish to collect them. Wish you all a safe journey back home and have great fun tonight, and hopefully I will see you again. Thank you very much for being with me. Hope it was worth your time. Thank you very much.